All right, let's get going. Okay, so there's been a lot of requests for seats. I don't know how many of you have, hopefully most of you have gotten seats in the class. We ran out. I've been telling everybody the same thing, that typically seats do free up. We did try to get some additional seats. I don't know if we're going to. Right now it's set at, I believe, 200. It's limited by the number of seats in this classroom. They will not open up more seats in the class than actually we physically have. So that's the limit. Now, what I've told everybody who's asked this question is that inevitably people drop and everybody gets in who wants to be in. It's just a matter of the timing, and I know that's not a great answer for you guys if you're still waiting to get into the class. Hopefully we'll have enough drops by Monday to accommodate everybody. The academic people are looking at how many seats are actually in this auditorium, and if there's enough, they will up it, but I don't know if they'll do that by Monday or when, what the sort of the time frame is on that. So anyways, I know you guys some of you are waiting. I get a lot of questions and emails about that. We're working on it as much as we can, but if they won't give us more seats, they won't give us more seats, and we can't do much about that other than wait for people to drop. Previous semesters, people have dropped at about maybe 30% of the classes dropped by the first couple weeks. So usually we do have enough to shuffle people around. It's just a timing issue. All right, so we've been talking about a variety of classifiers, and specifically we've been talking about decision trees last class. So decision tree is just a tree where at each node you have a decision point, and at the leaves you have a label. We started talking about how we're going to grow these trees. Basically, we're going to do it recursively. We're going to start at some root node using all of the data we have, and then we're going to keep basically applying the same procedure for each node to split it until we decide to stop. And we detailed reasons to stop last class. I'm not going to go into those again, but we were in the middle of talking about the gain. So the gain is just if we decide to do a split, how much of an improvement do we expect over not doing that split? So we break it into two pieces. The L piece is am I kind of loud here? I seem kind of loud to me. How's that? Good? Louder? Quieter? Perfect. Okay. The L piece here is the unsplit cell. It's sort of the we're specifically using entropy as our measure of how good the cell is. So L is our unsplit cell, which is just the negative sum of the probability of the labels of a label times the log probability of that label. So basically just the percentage of labels in that cell that are of a certain class. You sum over all of them and take this little formula. The S refers to after the split, the amount of information we have. So we just take the probability of going in the left direction, because when we split, some of the data is going to go left, some of the data is going to go right. We take all the examples that go in the left direction. This is the fraction that goes in the left direction times the entropy of that left cell. And again, this is just applying this formula for the data points that are in the left cell. You add that to the fraction that go to the right times the entropy of the right. You end up subtracting those two things, and you get a gain. And that gain is going to be for a specific feature and threshold split that we're talking about. So I'm splitting on the fourth feature, and my threshold is 7.5. So we're going to get a lot of different gains. So this takes us kind of to the procedure for splitting the node. So we're going to look at some number of features. When we build a tree, the first thing we're going to do is we're going to be building what are called random trees. And what that means is that we're going to start with some subset of random features. So we'll take all the features, however many there are, which is the size of the vector here. We're going to take the square root of that, and we're going to call that m. And then what we're going to do is we're going to, when we start building the tree, we're going to say we're only going to build this tree with some subset of the features. And that is this m random features. So for each of those features in the subset, we're then going to consider a bunch of thresholds t. Those thresholds are going to be any halfway point between an example in that cell. So if we, I think I actually forgot to include this. If we have a bunch of positive and negative examples in a cell, the thresholds we're going to look at are going to be the halfway points between those particular examples. So this is sort of the halfway point. This is the halfway point. So these would all be candidate thresholds that we're going to consider. So for each of the features, for each of the possible thresholds, we'll calculate the gain. Then we're just going to select the maximum gain. Now, if none of those gains are positive, if they're all negative, that means none of the splits were good, were better than just leaving the cell as is. We would just leave the cell as is. But if any of those splits are non-zero, we're basically going to take the one that has the maximum gain, and that's going to be the new split we're going to do. So we'll then apply that feature and threshold, split the data, and then recursively split those leaves if necessary, depending on what our stopping criteria is. So these two little comments down below, that's just talking about the thresholds, how we got those, and the random features, which is the m random features that we're considering when building our tree. All right, any questions on that? That's sort of our node building procedure. And that's really how we build a tree. Okay, a couple comments. We talked about this gain as our measure of how good a cell is. That is one of many different sort of criteria we could use to measure the goodness of a split. There's a bunch of different ones that the literature have over the years. Gain's a good one. It works as well as anything. There's no reason to choose one or the other than gain's just sort of a standard one. The other ones, people have tried to improve them, come up with different sort of split criteria. In general, you're going to see this one. Maybe you'll see some small variations of it. You don't have to worry too much about what the split criteria is. They're going to do the same thing as gain. They might do a slightly different calculation. So you don't have to worry too much about that. Let's see. All right, so now we want to talk about random decision forests. So a random decision forest is just a bunch of trees that are built, a bunch of random trees. So like we just said, we called that procedure, yes?
Sorry, this is about the slide before.
What was that?
This is about the slide before.
Oh, sure. What's up?
So it said return split for f is greater than t. What does that mean?
This just means that the new split criteria is, where am I? So let's say we're at this node. We got to split on some feature. So let's say it's x component 7, and it's greater than whatever threshold was the best threshold. So let's say it was 5.7. So that would be our new split criteria that we would use for that node. That's all I'm saying. Is that's what we're going to put on that node to do the actual split. Make sense?
Why do you keep split on random features rather than like whatever feature?
Okay, so we're not splitting on random features. We're splitting on the features that have the highest gain. Now, why do we use a subset of the features? We don't have to. We could create a tree with all of them. And in fact, if you were going to create a single tree, you would probably use all the features. However, we're going to do something right now, if there's no more questions about this stuff. We're going to do something right now that requires the randomness. And that is that we're going to create something called a decision forest. So instead of using a single tree, we can create multiple trees. And then we will vote, let's say we go to our data and we create 20 trees. We start from scratch 20 times. And then what we do is, if we want to predict a label, we give the data to each of the trees, the training example, sorry, the example, not possibly training, but an example to each of the trees, and they all get to vote. And 7 of them come up with the negative label, and 3 of them come up with the positive label. Then we would label it as a negative label overall. So in order to make this working, and this is often called bagging or ensembling, or there's a bunch of different terminology for this, the errors of the trees have got to be uncorrelated. So the trees need to be making different errors. And one way to make sure the trees are making different errors is to make sure that they were built differently. And that's where the randomness comes in on the actual feature selection, where we say, okay, this first tree is going to use feature 1, 7, and 9. The next tree can use feature 2, 15, and 6. The third tree can use a different set. They're all using different sets of features, and because they're all using different sets of features, we expect all their errors to be uncorrelated. And there's good theory that says that if you get a bunch of classifiers and you can show that their errors are uncorrelated, then taking the ensemble, sort of the group of them, and making the decision actually works extremely well. Like, really, really well. Like, it's amazing how much more an ensemble can do versus just a single classifier. So that's sort of the procedure we're going to do, is we're going to call it a random decision forest. And then what you do is train k random trees. And then to predict, we just vote with k trees. And again, it has to be random. If it's not random, if we weren't using a random subset of the features there, we'd keep getting the same tree over and over. If you were considering all features, the same tree would be returned every time because the gains would be the same every time. So it's important to randomize these somehow. Sometimes you randomize them using different data. Sometimes you randomize them using different features. Sometimes you do both. Okay, so let's talk a little bit about voting. We're going to have a couple different ways we can vote. Let's say we train 2 trees. And we train this one, it says plus, minus, plus. We train this one, it's minus, minus, plus, plus. Did I have 3 trees? I only did 2, so it'll be kind of dumb because we'll get a tie maybe. But and let's say that we want to predict an example. And so we come along and the example flows down this tree and gets to here. And so we'll say we have a score of a negative. Then we will do the same thing. We put it down here. It goes down this tree, and then we'll get a positive. Let's just draw a third tree just so my voting doesn't get a tie. And it goes down this tree, and we get another positive. So one way to vote would just be to count each tree as a single vote. That works just fine. And if you have a tie, you randomly choose a label. You could choose negative, positive, or if it's multiple trees, you might do multiple ones. Now, you often want to have the number of trees be quite a bit more than the number of labels, just so you get better voting. But this is losing a little information. Let's just say that I knew the number of examples that ended up in each of the leaves. And let's say that for the positives, we had 100 positives here and 0 negatives. We had 49. These don't even have to be add up to 100. They could be like, we had 7 positives and 8 negatives. Let's say this one, for whatever reason, had 50 positives and 5 negatives. And this guy, I think I actually wanted to do this the other way. Let's say this had 80, and then this guy had 5 and 3. And those are like the number of positives and negative labels. Now, we're always labeling with the majority class typically. So this is the majority class, this is the majority class, that's the majority class. But if we're doing some voting, we could vote by actually looking at, say, the number of examples that were in there. Because there's a lot more confidence in this and this measurement than there is in that measurement. So we could add up the number of votes for each of the class. So instead of just saying minus plus plus, maybe we say, okay, this one had 7 positives plus 50 positives plus 5 positives, and it had 80 negatives, 5 negatives, and 3 negatives. So maybe that makes sense. So you just add up the number of labels that were actually in the tree leaves. The third thing you could do is you could say, well, this kind of unfairly gives some advantage to some trees. So maybe we'll take the percentage instead of positive and negative. So the fraction of positive and negative. So the fraction of the label. All of these are valid voting criteria. In the end, if you have enough trees, if the number of trees you create is fairly high, it probably doesn't matter. There's no real good literature that says this is the right voting procedure for doing a forest. So in the end, you do whatever the software package happens to do, and you don't really worry about it. It's not even something that you generally tune. It's not something you're going to come along and be like, oh, I got to worry about voting, so I'm going to have a validation set to see what voting procedure I use. You just don't bother with it. It's not worth it. So just choose one, or whatever the package does. Does that make sense? Any questions on that? The only other comment I would say is that when you do random forests, it's actually really common to do really, really small trees. And so you might do a random forest where all of the trees are only 2 levels. So only 2 splits. But you might use 100 trees. So that will have probably more power than doing 2 trees with 100 splits. There's just this, a bunch of small trees generally will outperform a couple big trees. And that's real common. So just from a practical point of view, that's generally what you do. You guys do need to do random forests for homework 1, but you just need to go find a package and do it. You don't need to create your own. You don't need to write the gain functions. It'll just give you some experience with using a package. A lot of what we're going to do in this class, even though these first homeworks look like we're trying to make you write algorithms, we're really not. We want you to be taking libraries and using libraries. And so when you do your random decision forest, you're going to go find a Python library somewhere or an R library somewhere and just use it. And it's going to have a bunch of different things baked into it, and you probably don't even care most of the decisions that they chose for implementation. You probably don't even care about the details. All right, any questions on that? Okay, cool. All right, so now we're going to go to another form of classifier, and this is going to be the last type of classifier we're going to talk about before we move on to a whole new topic. So the classifier is called an SVM. It stands for Support Vector Machine. Let me write that down because it's an odd one. Support Vector Machine. So support vector machine is a linear classifier. So basically, we take we're going to take the feature space, and we're just going to split it in two. And we're going to split it in two with just a hyperplane. So it's just going to be a flat hyperplane. Now, it's worth talking about real quickly the different kinds of sort of decision surfaces that you can use with these different classifiers. And this is a fairly interesting topic. We've talked about four different types of classifiers. We have SVMs, we have a tree, we have a naive Bayes, and we have a nearest neighbor. So each one of these is going to split up the feature space in a different way. So like I said, a linear classifier is going to try to split it with a line. So it's a straight line. It can't curve around. It can't do magical things. It's just a nice straight line. Nearest neighbor is interesting because what nearest neighbor does is it basically forms, these are a little hard to draw because you got to draw the halfway points between things. Sort of this. So it forms sort of these cells. It's a little poorly drawn, but these actually go off to infinity. But each positive or negative, you're reporting the thing that's closest. So you're basically building up a little cell around the positive examples. So they can actually split the feature space in sort of these arbitrary ways. And that's fine. It's just a very flexible way of splitting the feature space. Now there's some downsides to that and whatnot, but it has probably the most flexibility of the way you split feature spaces. Trees, I think we talked about, we always make axis parallel splits. So if we're going to split, it's going to always be parallel to the axis. So maybe there's positives, that sort of thing. And then naive Bayes makes kind of these nice curves. So you'll often have sort of a curve, but they're sort of these continuous, I think typically they have to be basically sort of monotonic curves. I don't know all of the details of the different ways naive Bayes can build the things, but they're not sort of arbitrarily complex. They're sort of these nice curves, but they can't like weave in and out and go up and down and do all sorts of crazy stuff. So these are kind of the different ways that we split things. And you can see that we're actually classifying things in very different ways. This one's building little cells. This one's also building cells, but always breaking on feature axis. These ones are nice curves. These ones are actually very similar, except this one has to be a straight line. In the end, it's a little bit academic because you use the one that works the best. It's just good to know that there's certain cases that the vanilla algorithm like this isn't possible to, won't be possible to do something like you wouldn't be able to break up something like this. This is sort of a classic example of something you cannot separate properly with a linear classifier. A tree, you can easily separate this, but a linear classifier, any line you draw will not work because you'll always have, they'll always be incorrect. Nearest neighbor works really well with this. Naive Bayes probably would have trouble with this. But it's good to know that there are sets of data, like layouts of data, that will break. Now, in the end, we don't worry about it too much because we're going to do some tricks later on to get around this sort of limitation. All right, so back to support vector machines. So we're not going to model the probabilities. When we did naive Bayes, we did all this sort of work to sort of model the actual underlying distributions of data and examples and whatnot. We're not going to do that for SVMs. We're just going to create a plane that splits the data. So there's a couple limitations that we just want to note. No missing data or no missing values. So it's less flexible that way. Now, nearest neighbor, you really couldn't have missing values either. We're only going to be talking about real values. Although there's ways around that particular one. So no discrete values. And the other thing is we're only going to be talking about two classes. And specifically, we're going to call those classes -1 and +1. And that's just to make the math work out nice later. If you call them -1 versus +1 instead of 0 versus 1, the math becomes a little easier to write out. And you can use some nice mathematical tricks to write things concisely. But still, the limitation is really that we're only going to be using two classes, which is unlike most of the other ones. Okay, so what are we going to do? We're going to learn some linear function. And that linear function, like I said, is going to be a hyperplane that just splits the feature space. So what do I mean by that? Let's just look at a two-dimensional example to start with. We have a single feature that we're going to call x. We can draw a line in here. Now this line is some ax plus b. I don't know why I'm writing from that side today. I seem to be very awkward today. Ax plus b. And what we're going to say is that anywhere this ax plus b is positive, we're going to call that a positive example. And anywhere it's negative, we're going to call it a negative example. So in the one-dimensional case, basically everything over here is going to be a plus, and everything over here is going to be a minus. So we've just taken a linear combination here, split the space in two, and use that. Now let's look at it in 2 dimensions. This one's a little harder to visualize because what you're going to have is 2 components. So we'll call this x1 and x2. And what we're interested in is, again, the spot where basically your decision point is sort of this point where this is where ax plus b equals 0. And we want the same thing, is in this 2-dimensional space, what's going to happen is there's going to be a plane that sort of slices through this at some angle. And the way we're going to draw this is we're going to draw the line, some dotted line, and this is the line ax plus b equals 0 of some plane. I don't know how to even draw this. This is part of a plane that is sort of slicing through the two-dimensional thing. So the plane is coming out into 3 dimensions. Does that make sense? It's sort of like if this was our 2 dimensions, we're going to come up with a plane that, kind of cuts through it. And then again, on one side of this, we're going to call everything positive. This is the side where ax plus b is greater than 0. And over here, we'll call everything negatives. And this just, in higher dimensions, it's the same thing. It's a hyperplane of some n dimensions that's slicing up your feature space. Questions on that? This is a little hard to visualize. We'll typically look at this picture and not this picture. Just so when I draw a line, I generally mean that on one side it's, this is the plane, the zero plane, where the plane is equal to 0 in this space, and on one side it's going to be positive, the other side it's going to be negative. All right, so like I said, we're going to just come up with some a, which is a vector. It's going to be the size of the feature space, and some b, which is sort of our intercept to allow us to sort of move the thing around. And we're going to choose those a and b such that the sign of ax plus b, that's probably a transpose, is the class that we're going to use. And we're going to choose it such that this will be our class, positive or negative. And then we're going to minimize some error function. So we're going to choose these a's and b's, so that they minimize some function. And we're going to make up that function. And different functions are going to result in different a's and b's. And basically, the different functions that you could minimize are going to correspond to a bunch of different linear classifiers that exist out in the world. We're going to talk about SVMs right now, but there are many different linear classifiers that we could talk about. And we will later on, actually, when we get to regression, talk about different kind of linear classifiers or different kind of linear functions and error functions. Okay. So let's talk a little bit about the error function that we want to use. We often call this the cost. It's how much we're going to pay for making mistakes. So to rewrite this, I want to minimize some a and b, choose some a and b such that it minimizes some cost on the training set plus lambda, some cost on the future errors. So what we're saying here is we want to take not just into consideration the actual training cost, we're going to pay a penalty if we're getting things wrong on the training set. We also want to sort of have this second component that says, well, let's try to make sure that we're also going to do okay on future errors. Now that's going to be a little tricky because we don't have future data. So we're going to have to come up with some sort of guesstimate of this cost because we don't actually have data to drive that. So this is sort of going to be a heuristic to control for future errors. This is going to be some cost that is associated with the actual training set. The cost of the training errors, this is just going to be an average over the cost of individual examples. For all the examples. So that one's really easy. And in this case, we will often write this just as a, we're going to write it like this. For I element of an example, and we're going to write the cost as the cost between the true label in the data and some gamma I, where the gamma I is going to be our A transpose X plus B. So that's just how we're going to write it, is our cost function is always a cost of basically this guy drives what our predicted label is, this guy is our actual label, so the cost is going to be something that compares the two, and if you're right, you get some, hopefully no penalty. If you're wrong, you get some penalty or cost associated with it. So let's talk a little bit about how we might come up with this cost. This cost is something that, like I said, different types of classification could come up with different costs, and they would generate different boundaries, and they might work better or worse. But the ones that we really care about is the one that we're going to talk about right now for SVMs. There's a couple criteria. So if, let's draw this out. I'm using a lot of paper today. A little worried about running out. So if we have some decision boundary that we came up with, and our prediction was if this is the positive side, and let's see, this is the negatives. If everything on this side is what we're calling positive, and we get a negative over here, what we're going to want is a cost that's fairly high. So this is something where the sign is incorrect. Basically, I have a negative, it should be a positive, or rather, I predicted it as a positive, it should be a negative. I want the cost to be high. Same thing if I had a positive over on this side and I predicted it as negative, I want the cost to be fairly high. And the other thing is, this will have a score. For any given example, we're going to have a score of AX plus B. As that magnitude goes up, we want to have a higher cost. So basically, as we get it more and more wrong, we want that cost to go up bigger and bigger. Now, if they have the same sign, which means that we predicted it correctly, and the magnitude is fairly small of the actual prediction, AX plus B, we actually want to still assign a small amount of error. And so we're going to have kind of an area around this line, this prediction, where even if I'm predicting it as positive, it is a positive, but it falls somewhere near the line, I'm still going to give a small penalty. This is often called a margin, this little thing around it. And that's basically to say, I want to give myself a little leeway where, sort of a buffer zone around which, I don't want things to lay really near that decision boundary. I want to push, my predictions away from that decision boundary. So we're going to want to have a non-zero error even if we have it right sometimes. And then if we have it right, if we have the sign correct, we don't want to pay a cost. If we get, if it's a positive and we predict positive, then we're fine. We don't really care about that. All right, so let's look at the actual, I have enough room on here. Let's look at the actual function that we're going to use. So the cost of an example versus our gamma is going to be the max of 0 and 1 minus y. Remember, y is either 1 or negative 1, so it's the label, but it's a integer of 1 or negative 1, times the gamma. So this is something called a hinge loss. And even though we've been calling them costs here, they're often called losses. So let's look at what this looks like. If this is, let's see, if this is gamma equal to ax plus b along this axis, and we have some cost of y lambda along this axis, if y is equal to 1, we get a line that looks something along this way, where it crosses here, comes up there, and the cost is 0 over here, and it's non-zero over here. So this is why they call it a hinge loss, because it looks like a little hinge. And again, this little section in here is the case where we've predicted the correct thing, but we're still going to pay some cost for it, because we really want to give ourselves a little buffer to give ourselves a better classifier. And then it should be noted that this just goes up linearly forever. So if you're really far away from the decision point, you can get a fairly big cost. Questions on that? Now, for the case of negative, y equals negative 1, it's just the opposite. The math just flips around, but conceptually, it's the same thing. It's just flipped over the axis there. All right. So that's the cost we're going to use for our training error. Now we should talk a little bit about the future error. Future error is a little bit tricky because we don't have future data. I mean, we can't have future data because we don't have it yet. It's from the future. But we still want to somehow think about how we could maybe generalize towards the future. And the way we should think about this is, well, one way to think about it. There's a couple different ways to view this, and the book talks about a couple different ways. But and if you go out and you read sort of Wikipedia and whatnot, there's a lot of different ways to describe this. The one that I like is, let's assume we have a classifier that correctly classifies everything. And we have some positives, and we have some negatives. And now we can draw this line. If this is our AX plus B. AX plus B equals 0 point. Now the interesting thing is that the scaling on A and B are arbitrary. Like, we can rescale A and B and keep this plane in the same spot. And so we could just have A is equal to some scaling times A, and B is equal to some scaling times B. So basically there isn't a unique solution here for the same cost and for that same sort of plane that we're going to break it on. But we can kind of think about what happens if an example is really close to the boundary. let's say it's right here. Now, we normally have a cost of 0 if it's correct. But let's say this is a future one, and we get it wrong. We haven't seen it yet, but we have a good classifier. We haven't seen this cost, or sorry, we haven't seen this example yet because it's a future example. And this one we happen to get wrong. So if we scale up A sort of arbitrarily, this cost right here of getting this one wrong scales with the size of A. So the bigger A is, the more the cost on future data that we'll have to pay. Because now we've made a mistake that if we make A very small, is going to cost us very little. If we make A really big, it's going to cost us a lot. Now, we don't know that point. We haven't seen that point. We'll never see that point. This is an imaginary point, sort of, not imaginary, but some future point that we might encounter. But this is just sort of the logic of working through how you might come up with one of these costs. And so the sort of what this suggests to us is that we should pay some cost for the size of A. And the bigger A is, the more the cost we should pay. And for that matter, we could pay a cost on B. It doesn't matter because of it all sort of works out in a wash if you pay it on B. But we're going to pay the cost on A. And so for that, we're going to come up with a new formula. Our overall cost of y versus some gamma is going to be equal to, these are just the two parts I wrote before. This is our cost on our training data. 0, 1 minus yi, gamma I. And then we have the cost on the future error. And we're going to use what's called A transpose A. Now remember, A is a vector here. Because it's a vector, anytime you do A transpose A, you're basically taking the square of the magnitude. So you're just taking the vector and squaring basically the length of it. And so we're going to pay some cost associated with the size of this A. Now you might ask some questions. Why is there a 2 here? That's just because later on we're going to take the differential of this, and if we put a 2 there, the differential of a square cancels out a 2, so the math will work out nicely. We also have this lambda here. Lambda is a hyperparameter. It's a parameter we're going to have to choose. We're going to have to say we want to trade off sort of the cost of our training error versus the cost of our future error. And we have some control over how we trade that off. We can say we really want to make sure our future error is taken care of, but we don't have a good estimate of that error. Or we can say we really want to take care of our training error. We want to pay the lowest cost for that and ignore future error. So we kind of have this lambda parameter that trades off the two. If lambda is high, then we're saying let's try to generalize to future error more. If lambda is low, it says let's make sure we get the training error as correct as we can be. Now, like all hyperparameters, when we train our SVNs, we're going to have to choose this hyperparameter. And just like when we had to decide on, say, the distributions we're going to use for building a naive Bayes, we're going to want to have a validation set that allows us to choose this. And so what we're actually going to do is we will, like we draw all the time, we'll set aside some test set. Then, with the remaining data, we're going to set aside a validation set. And that validation set is going to be for lambda. And then this will end up being our training data. And the procedure we're going to use for choosing lambda is just guess on what some lambda values can be. Typically, they're things like 1, 0.1, 0.01, down to, I don't know, maybe a little smaller. So you usually take orders of magnitude right around 1. And then for each one of these values, we'll train a separate model on this training data, and then we'll use this validation data to determine which lambda we like the most. Now, like everything, we could do cross-validation in here if we need more statistical power. If we're limited on the amount of data we have, and so we want our validation to have more statistical power, we could do cross-validation inside of this sort of tuning loop. Depending on how much data, you may or may not care to do that. Generally, you don't need to for lambda, but if you only have 100 data items, you'll probably end up doing cross-validation within this little section. All right. All right, questions so far?
So you said like if you're more wrong, you're the further away you are from being right, it's a higher cost. Where is that in the cost structure?
That is, where am I? This guy is the cost function. This guy is going to be our estimate. So so the gamma is this. When this is greater than 0, we call it a positive. When it's less than 0, we call it a negative. And so the magnitude of this value is going to determine, basically, as that gets bigger and bigger, that's going to increase the cost. Now, if it's correctly categorized, you basically don't pay a cost, except for that small margin region right there. You end up not paying a cost. But you keep paying a higher cost because this value keeps going higher and higher as you get more and more incorrect. You get farther and farther from the line. So in this particular guy, if this is the AX plus B equals 0, if you have a positive way down here, this has a very negative, it's sort of distance this way, has a very negative AX plus B, and that's where that cost comes in. Good? Cool. All right, anything else?
So how does scaling how does that reduce future data errors?
Okay, so that's the one that's really hard to describe. It's sort of, we're making this sort of really abstract argument that, okay, let's say we had a perfect classifier, and we make a very small error on on future data. If we know we've made an error on future data, the larger that A is, the larger that cost is that we're going to pay. Now, we're not actually integrating that into the function directly, but we're sort of saying if I have the bigger A is, the farther this value will be from the decision point here. So if I'm making a mistake and I make A very big, it's going to be, instead of being right here, it'll be way out here. If I make A even bigger, it's going to be even farther out. And so now we don't know this point. We don't have this. We're just saying let's suppose we did make a mistake. If we did make a mistake and we have a very large A, we know that on this future mistake we're going to pay a really big cost. And so that's sort of the intuition behind, well, maybe we shouldn't make it a big A. Maybe we should make sure that A is small so that if we do make a mistake on some hypothetical future data, the cost of that mistake will be small. Does that make sense? Yeah, it's a little bit of a fuzzy argument that, we don't have any data, but if we had data and we had a large A, then the cost would be really big. So there's other arguments on why it should be that size. That's the one I like. It's the most straightforward, I think. But you can actually go and find a lot of people who argue different reasons on why this A should be fairly small. In the end, everybody agrees that the A should be fairly small. That's not a question. How you penalize it does change a little bit. You can make different arguments on how you apply that penalty. Here we talked about A transpose A, which is the square of the magnitude. You can pay that penalty differently. And we'll talk about that in the future, different penalties that we might use for future data.
Why do you have to build a penalty into the cost function? Why couldn't you as you're fitting just keep rescaling A and B down to a small value?
Well, essentially that's what you're doing. But you have to have some systematic way of doing that, right? You have to make a choice of how to do that. We could. So you will actually, as A gets too small, you will start making mistakes on the training data. So if you set A to be all zeros, then you're always going to make a mistake on the training data. Well, let's say B was 0. You'll always have a penalty on the training data. So there is a cost associated with this. There is a trade-off between these two things. Too small of an A, and you're not going to be able to categorize anything correctly. Too large of an A, and we think we're going to have some future data mistakes that cost a lot. So that's why it has to be in the cost function itself that you're minimizing. You can't just arbitrarily rescale down, because changing A actually does have an effect on how you categorize things and the what you pay for it. All right, I think there's one more here.
Can we claim that the major difference between these and logistical regression is different loss functions?
Yes. We haven't talked about that yet, but yes. Logistic regression, there's a whole nother thing going into logistic regression that we won't talk about until after we talked about regression. There's a whole nother mechanism that works there that's actually really interesting, but we won't get to that until for another 3 weeks or so, when we talk about actual logistic regression. Still turns out that it's a linear classifier. It's very different on how you formulate the loss function and how you train it. Anything else? All right. Oh, one more.
The increase of A, is it related to overfitting of the data in some way?
Yes, very much so. One of the reasons we're paying this cost on A is because let me take that back. Let's see. Is it relevant to overfitting? Certainly it is, in that it will help you generalize by keeping A smaller. Now, the reason I can't think off the top of my head the direct connection between that, but certainly it is a factor in generalization that you want to keep the A smaller. But I don't have a good answer for that, I'm afraid. I'd have to think about that for a second to see how those two things come together. Now, certainly the margin that we pay on the hinge loss, that is definitely part of avoiding overfitting. That's saying we don't want things near our boundary. We really want to push things away from our boundary. So that definitely has a direct effect on generalization. But the A also does. Was there another question up here?
If you didn't have this cost of future errors, could you get 100% on your training data?
Yes. Well, maybe. It depends on if your training data is linearly separable. I mean, I showed that grid area of earlier of plus, plus, minus, minus. You can never get zero error on that. You're always going to get one of them wrong because there's no way to take a line and split. That's like the canonical example that you just can't do. But anything where the positive and negatives are sort of mixed in, a linear classifier is never going to work in that case. I mean, we're going to do things to make it work, sort of, but in the, if the feature space is set up like this and we're building a classifier in this space, there's no way we can split this to make sure, and likely it's going to be something more like this, is the linear classifier we'll come up with is something that's going to split here, and that negative will be incorrect. Data's messy. It's going to, there's no perfect answers for a lot of things. And maybe that's, there might be a lot of reasons why that particular negative is in the wrong spot. It might be bad data collection. It might be a weird, if we talk about, later on we're going to talk about salary data, and maybe somebody got really lucky. Nothing in their history showed that they should make a lot of money, but they got lucky and got a really good job. That kind of stuff does happen. And data is messy, labels are messy. Sometimes they're mistakes, sometimes there is no boundary. And sometimes if there's a bunch of, big clusters of negatives in here, maybe that shows that there's actually some interesting thing going on where there is sort of some structure to the space that a linear classifier is just going to have trouble with without doing something special. Anything else? Let's see. Okay, cool. All right, so that's all the easy part. Now is the hard part. How do we come up with A and B? We wrote a cost function. We want to come up with an A and B that minimizes that cost function. But we still have to come up with it somehow. And so what we're going to do is use something called gradient descent. Now, gradient descent, I think most of you have probably heard about this. If we have a function, let's just say this is our function, some wacky, bouncy thing. Gradient descent is a process in which we make iterative estimates and try to improve them. And the way that we're going to try to improve them is, let's say we start here with some initial estimate. We just guess some place to start often. The way that gradient descent is going to work is, let me draw this in a little different color. You're going to just look at the direction of the gradient and take steps in that direction. So when I say, it's right here, that means the data point right now is right here. And so I look, I say I'm going to take a step in sort of this direction, and I end up moving this way. So maybe I get a new data point right there that corresponds to this. This is going to have some gradient, and I'm going to move in that direction. And I'm going to keep taking these steps until I find some minimum, until things stop changing so much. Now, there are issues with this. If I started over here, I can get stuck right here. So this only is guaranteed to work for convex functions. It happens that we're working with a convex function right now. We won't in the future. We will actually move to non-convex functions. The other thing is this doesn't really, the derivative doesn't really tell us the rate of change of the derivative itself. So it may be that we're at a point where the derivative is one thing, but the derivative is changing a lot. So if we're in a really wiggly area, so let's say we had a function that was some crazy, up, down, 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 up, down. Now at any given point, our derivative is going to be in some direction. But without looking at the second derivative, we don't really know how fast that derivative's changing, so we don't really know how long of a step to take. And that's going to be an issue also. But the general concept is we kind of look at the gradient, we take a step in the negative direction of the gradient until we're really not moving anymore. So let's look at that in sort of a mathematical form. 10 minutes, okay. First things first, we're going to say we have some u, and this is just going to be a vector with our parameters concatenated. These are, by the way, when we talk about vectors, we're always talking column vectors. So anytime we start doing matrix multiplication or anything, we're talking column vectors unless otherwise noted. So this is a column vector with b stuck on the end. And we're going to do that just for convenience sake. And then we're going to have our function, some f, and this is going to be some f, and it's going to take your current, it's going to be an input of your current, of a training example, but it's also going to have some input of this u, sort of the current u, and this, again, is just the 1 over max of 0, 1 minus y I, sorry, there's a sum in there, lambda I plus, sorry, that's gamma I plus A transpose A. So we have some function. This is our cost function that we've been talking about this whole time. Now, how do we minimize that? So we are going to start at some u0. This is just some initial spot we start at. And this is, just so we have it down, this is gradient descent. We're going to start at u0. We're going to compute the gradient with respect to the parameters a and b, which we're calling u here, of f. And we're going to evaluate that at our current iteration, whatever our current u estimate is. And then we're going to update our u estimate. So u of r plus 1 is just going to be the current u. And then we're going to take a small step in the direction of the gradient we just calculated, again evaluated at r. So basically, this is just what I had drawn out. We're going to start somewhere. We're going to compute that gradient. We're going to take a small step in that direction. This eta is just there to control how big of a step we take. If we take too big of a step every time, we'll just bounce around the space. We'll bounce back and forth even if we have just a nice parabola. If eta is too big, we're going to go back and forth on either side of the valley repeatedly, possibly getting worse and worse each time even. All right. So a couple comments on this. First thing you should think about is taking the differential of the f function has a problem. You'll notice that there's a max in there. And it's the max of that hinge loss function. The point of the hinge, where it takes that sort of angle, the derivative is undefined. There's just no good derivative there. Sorry, that's a poor statement. There is no defined derivative there. In the end, we don't really care. You could take the left or right derivative. They both turn out to be, basically 0. So if you really come up with if you hit right at that hinge position, you would just call it a derivative of 0. So we don't really have to care about that. It's interesting that you can have a differentiable function and still do this just fine. But that is a problem on some functions, not on this one. Oh, by the way, this is, in case it wasn't clear, we loop here. So that's sort of the basic gradient descent. Now, gradient descent works real well. There's some conditions we're going to talk about for selecting the step size, how big of a step we take each time, and whatnot. But the bigger issue is going to be that with really large data sets, gradient descent becomes impractical. The problem here is that gradient descent requires us to evaluate the derivative of f. The derivative of f is a sum over all data points. Even after we take the derivative, we're still going to have that sum over all the data points in there. And so the issue with gradient descent is that as our data set size increases, it's going to become more and more costly to take these steps. And there's going to be a point where it's just prohibitively costly to take a step, because if you have a billion data points, and that is not, that's internet size data nowadays is billions of data points. You certainly cannot sum over a billion data points each time you want to take a single step towards a better estimate of U. So we're going to have to do something to get around that. And the thing we're going to do is we're going to make an estimate of f by sampling. And it's fairly straightforward. I can just show it here. Instead of taking a sum over this, over all of the data points, we're going to take an average over a sample of the data points. So instead of saying we're going to do 1 over n of the max, sort of the sum of 1 over n over the sum of all, we're going to take a sample here. And we're going to take a sample of size NB. And that's called a batch, by the way. Instead of taking a step that's based on the whole data set, we're going to take a step based just on this subsample. Now, the nice thing is that, and this is proven in the book, or at least demonstrated in the book, that in expectation, the value of this sort of sample that we're going to take of however many small number of data points that we're going to average over, in expectation, that has the same gradient and same value as the full data set. Now, there's variance there. It's going to make mistakes sometimes. It's going to go in the wrong direction sometimes. But in general, it's going to go in the correct direction. And it's going to allow us to do very quick steps that take very little time, even if our data set is prohibitively large. And this is going to form something called stochastic gradient descent. Stochastic meaning random, so we're going to take these sort of random steps. But in expectation, we're going to go in the right direction, and we're going to come up with the correct answer. Question?
So normally, what percentage will that sample be?
Okay, so we'll talk about that probably on a while from now, but I don't have anything else, so I can talk about it real quick. It could be as small as a single element, a single example. Often it is dictated by the efficiency of your compute. So if you have, if you're running on a GPU and the GPU can handle chunks of 256 really well, we'll take 256 at the same time. But small. We're talking small. All right. Anything else before we go? All right, there's a homework due on Monday night, so you should probably have looked at that already. If not, have a good weekend, I guess. And I'll see you guys on Tuesday. Bye.